Good morning, everybody, and welcome to SciQuil. I'm your host, Cy Wraith, and this is another edition of Daily Science News. Today, I would like to talk about fusion research at the JET facility. This is an article from phys.org written by Eurofusion on February 8th, 2024. Fusion research facility's final tritium experiments yield new energy record. The Joint European Torus, otherwise known as JET, one of the world's largest and most powerful fusion machines, has demonstrated the ability to reliably generate fusion energy while simultaneously setting a world record in energy output. These notable accomplishments represent a significant milestone in the field of fusion science and engineering. In JET's final deuterium-tritium experiments, DTE3 otherwise known as, high fusion power was consistently produced for 5 seconds, resulting in a groundbreaking record of 69 megajoules using a mere 0.2 milligrams of fuel. JET is a tokamok, a design which uses powerful magnetic fields to confine a plasma in the shape of a donut. Most approaches to creating commercial fusion favor the use of two hydrogen variants, deuterium and tritium. When deuterium and tritium fuse together, they produce helium in vast amounts of energy, a reaction that will form the basis of future fusion power plants. So I've got a little piece here to show you. So what is fusion? Fusion is the energy process that powers the sun and other stars. The fusion reaction between deuterium and tritium produces helium and a neutron with a high energy level, which can be used to heat the steam cycle of a power station for generating electricity. This process is so powerful that the fusion of all atoms in 1 liter of deuterium-tritium gas mixture would create roughly enough energy to cover the yearly needs of an average-sized house. Pretty impressive. So to explain that in better detail, this is an image showing the process. This little positive here is your proton. This is your neutron. This is the nucleus. Normally, a hydrogen atom is strictly this. It's just a proton with one little electron flying around it. There is no neutron. But in the case of deuterium, it has a neutron. So this is what we call an isotope. We've also got a second isotope here called tritium. It has two neutrons, still one proton. This is significant because when we want to fuse them together, protons are going to repel each other. They aren't going to do that without neutrons to get in the middle. The neutrons help balance out that repulsion so that you can actually build a new nucleus. And so that's why we have to use these isotopes that actually come with the neutrons. And in that process, one neutron escapes, and we end up with a 2 neutron, 2 proton helium atom, a completely new atom. It's like converting hydrogen to helium. It's essentially the process. And when that's done, you have a big source of energy produced. So to make fusion happen, the positively charged nuclei have to be provided with enough kinetic energy and thus high speed to ensure they can overcome their mutual electrostatic repulsion at the time of collision. So these two protons, as said, they will repel each other. So to get them to fuse is going to be like trying to put two magnets of the same polarity right up against each other. If you've ever tried to do that, they fight each other. They won't go close. So you need a lot of energy to get them to go together. That's essentially what's going on here. To achieve this high level of kinetic energy, a hot gas, or otherwise known as a plasma, has to be heated to a very high temperature of over 100 million degrees, which fuses nuclei together. While the sun's gravity is able to hold the hot plasma, on Earth, magnetic fields are needed to confine the plasma. So the sun does this naturally with its own gravity. Since it's such a large mass at the center, it actually does fusion naturally. And that's how the sun produces heat. Here, we have to use magnets to produce that sort of same effect as gravity. You can imagine those are very powerful magnets. And the machine that does this is actually called the tokamok, which it's mentioned in the article right here, the tokamok. So this is the design style. And you can see a piece of it here, and you can see a better explanation of a tokamak here. So since the 1950s, scientists have been investigating different ways to confine the plasma with magnetic fields. In magnetic fusion, the plasma is in a ring-shaped container called torus, this section here, where strong magnetic fields keep it away from the walls. The tokamak configuration upon which JET and ITER are based has been the most successful yet. So right, this 100 million degree plasma can't touch the walls. It has to be in the air only. As soon as it touches the walls, of course, you're going to have damage, melting of components, melting of the walls. That would probably not be a good thing. There's another one here called the stellarator. It is an alternative concept to the tokamak. Due to its complex magnetic field, the construction of this device is highly challenging, but this design is in principle suitable for continuous non-pulsed operation. This experimental device, Wendelstein 7X, has recently been completed and is operated by the Max Planck Institute for Plasma Physics in Greifswald. I hope I've pronounced that properly. Anyway, so you can see that the tokamak is not the only option, but right now it seems to be the most common and best one. Dr. Fernanda Rimini, JET Senior Exploitation Manager, said, quote, "We can reliably create fusion plasmas using the same fuel mixture to be used by commercial fusion energy power plants, showcasing the advanced expertise developed over time," end quote. That's pretty good. Down here, Dr. Emmanuel Joffrin of Eurofusion, Tokamak Exploitation Task Force leader from CEA, said, quote, "Not only did we demonstrate how to soften the intense heat flowing from the plasma to the exhaust, we also showed in JET how we can get the plasma edge into a stable state, thus preventing bursts of energy reaching the wall." Okay, so plasma is also very erratic. It's going to have little pockets of energy flying off in different directions, which can also cause damage to the walls. So they were able to contain that better. Both techniques are intended to protect the integrity of the walls of future machines. This is the first time that we've ever been able to test those scenarios in a deuterium-tritium environment. Over 300 scientists and engineers from Eurofusion, a consortium of researchers across Europe, contributed to these landmark experiments at the UK Atomic Energy Authority site in Oxford, showcasing the unparalleled dedication and effectiveness of the international team at JET. 300 scientists, it's a good team. The results have solidified JET's pivotal role in advancing safe, low-carbon, and sustainable fusion energy. The UK Minister for Nuclear and Networks, I had no idea there was such a minister, his name is Andrew Bowie, said, quote, "JET's final fusion experiment is a fitting swan song after all the groundbreaking work that has gone into the project since 1983. We are closer to fusion energy than ever before thanks to the international team of scientists and engineers in Oxfordshire." That's exciting. Quote, "The work doesn't stop here. Our Fusion Futures program has committed 650 million pence to invest in research and facilities, cementing the UK's position as a global fusion hub," end quote. JET concluded its scientific operations at the end of December 2023. JET's research findings have critical implications not only for ITER, a fusion research mega project being built in the south of France, but also for the UK's STEP prototype power plant, Europe's demonstration power plant, DEMO, and other global fusion projects pursuing a future of safe, low-carbon, and sustainable energy. Dr. Pietro Barabaschi, who is the ITER Director General, said, quote, "Throughout its life cycle, JET has been remarkably helpful as a precursor to ITER, in the testing of new materials and the development of innovative new components, and nowhere more than in the generation of scientific data from deuterium-tritium fusion," end quote. JET has been instrumental in advancing fusion energy for over 4 decades, symbolizing international scientific collaboration, engineering excellence, and the commitment to harness the power of fusion energy, the same reactions that fuel the sun and stars. JET demonstrated sustained fusion over 5 seconds at high power and set a world record in 2021. JET's first deuterium-tritium experiments took place in 1997. As it transitions into the next phase of its life cycle for repurposing and decommissioning, a celebration in late February 2024 will honor its founding vision and the collaborative spirit that has driven its success. The achievements at JET, from the major scientific milestones to the setting of energy records, underscores the facility's enduring legacy in the evolution of fusion technology. Its contributions to fusion science and engineering have played a crucial role in accelerating the development of fusion energy, which promises to be a safe, low-carbon, and sustainable part of the world's future energy supply. Fusion, the process that powers stars like our sun, promises a clean baseload source of heat and electricity for the long term, using small amounts of fuel that can be sourced worldwide from inexpensive materials. When a mix of 2 forms of hydrogen, deuterium and tritium, is heated to form a controlled plasma at extreme temperatures, 10 times hotter than the core of the sun, they fuse together to create helium and release energy which can be harnessed to produce electricity. Here's an interesting look at the inside of the tokamak. Deuterium and tritium are 2 heavier variants of ordinary hydrogen and together offer the highest reactivity of all fusion fuels. At a temperature of 150 million degrees Celsius, deuterium and tritium fuse together to form helium and release a tremendous amount of heat energy without any greenhouse contributions. Fusion is inherently safe in that it cannot start a runaway process and produces no long-lived waste. There is more than one way of achieving fusion. Our approach is to hold the hot plasma using strong magnets in a ring-shaped machine called a tokamak. and then to harness this heat to produce electricity in a similar way to existing power stations. So they would produce steam or something, move some sort of turbine, and that's how you would get the electricity from that. I wanted to go into the difficulties that they've had with this. One of them would be the pricing of tritium. So here you see that it takes about 300 grams of tritium per day to produce 800 megawatts of electrical power. Now, to get 800 megawatts compared to the Three Gorges Dam, this is 22,500 megawatts. So it's 8 versus 22.5 megawatts per day. Actually, that's per hour here, I believe. And the cost of 300 grams of tritium, well, $330 here in Canadian dollars for 5 grams. You can see that's going to cost about $20,000. About $20,000. So what we need to do is increase the amount of energy we're producing, reduce the costs of tritium, and make, obviously the most important one is a sustainable plasma that is controllable and with many of these tokamaks in unison running all day long. 5 seconds is what they have accomplished, is a start, but that's still far up from where they need to be in terms of sustainability because they'll need to be running this all of the time. Anyhow, let me know what you think about this. It's very exciting, I think. We obviously need sustainable energy. Wind and solar help, but considering their costs and what we are getting out of them, the world needs more. That is clear. We still rely heavily on oil, although every step in this sustainable direction, I think, is a good thing. And fusion would be, if possible, the best version of sustainable energy and would lead to who knows what in the future, a revolution of sorts for technology in general. So, yeah, let me know what you think in the comments. Please like and subscribe, and I'll see you in the next video.